Chapter 8 is going to be about working with systems of equations and systems of inequalities. Now, I've created lecture videos and assigned homework for just two sections in Chapter 8. That's 8.4 and 8.5, and right now we're looking at 8.4. Okay. I just want to point out that 8.4 is about systems of nonlinear equations. Nonlinear just means that if it's an equation in two variables, its graph is not a line. Okay, so it's going to be a more complicated equation. Its graph is going to curve in some way, shape, or form. Now, 8.1, which we're not really spending much time on, is about solving systems of linear equations. That's essentially review, and so I haven't assigned any homework for that. But we're going to use the same techniques for solving our nonlinear systems that you've learned in previous classes for solving linear systems. So each time I introduce a technique, the first example that we do is going to be a linear example. And then we'll move on and apply that technique to the more complicated nonlinear examples. Okay. If any of you feel like you want more practice with either of the two methods we're going to use, the first method is the substitution method. That's what we're going to do in this video here. Okay. If you want more practice with linear systems, by all means, feel free to look through 8.1. You can find linear systems in the homework for 8.1. If you want me to recommend a few problems, if you feel like you need some more practice, I'm certainly happy to do that. Okay. All right. So, as I said, the first method we're going to take a look at is the substitution method. Let's start with a linear example. So let's suppose I have x plus 2y equals 5 and 3x minus y equals 1. Now, just a reminder of what it means to be a solution to a system. This is a system of equations in two variables, x and y. So a solution would be an ordered pair, an x and a y value, that make both equations true. Now, graphically, a pair of values that makes this equation true would correspond to a point that's on the graph of this equation. And since this is a linear equation, its graph is a line. So a solution to the first equation is a point on the first line. Similarly, a solution to the second equation is a point on the second line. So a solution to the system would be a point on both lines, or a point where the lines intersect. So that's essentially what we're trying to find. Okay. Now, with the substitution method, I'm going to work out this example over here. As I do that, I'm going to record the steps that we use over here. And the steps are the same whether we're working with a linear or a nonlinear example. Always the first thing I'm going to do is pick one of the equations and solve for one of the variables. Now, I think the simplest thing in this case would be to work with this first equation and solve for x. The reason I like that is because the coefficient in front of x is just 1. So notice, if I solve this for x, all I have to do is subtract that 2y over. So x would be 5 minus 2y. Compare that to if I solved for the y, I'd have to subtract over the x, but then I'd also have to divide by 2. And that would introduce fractions. Now, I can work with fractions, certainly should be able to at this point in my math career, but this is kind of nice because I don't have to at this point. I think the other simple choice to make would be to solve for y in this equation. Now, its coefficient is -1, but I could solve for y without introducing fractions. I would have to deal with that negative sign either by moving y to the other side or by multiplying or dividing by a -1, which would change some signs, okay, but I wouldn't introduce any fractions. Okay, so step 1 is to pick an equation and solve for one of the variables. Okay, and I just say here, pick an equation. I don't usually do that by flipping a coin. I usually do that by employing some strategic laziness to say, what's the easiest variable to solve for that preferably doesn't involve introducing fractions? Sometimes fractions are unavoidable, but if they can be avoided, it's worth trying to. Okay, then what this does is this incorporates all the information about x, y being a solution to this equation. But I need it to be a solution to this equation too. So what I'm going to do is take this expression for x and plug it into the other equation. Now, it is super, super important when you plug this back into one of the original equations that you plug back into the other equation. If I plug this back in for x here, I'm going to create an identity that's always true, because this information and this information are exactly the same thing. I want to use the information that, hey, I need to be a solution to the second equation as well. Okay, so step 2 is going to be to plug the result of step 1 into the other equation. So let's just see what that looks like. That would become 3 times x gets replaced with the quantity 5 minus 2y, and then minus y is equal to 1. Notice the result of this, I've got an equation in just one variable. Cool. So I'm going to even write that down. The result will always be an equation in one variable. Now, because with this example, we're looking at a linear system, the result is a linear equation in one variable. When we move on to nonlinear systems, that might not necessarily be true. So we might have some more complicated sorts of equations to solve. That's okay. Once I've got this, my next step is to solve it. Okay. So I don't have a whole lot of space here. I'm going to just erase the preceding work. To solve this, I would first of all just distribute that 3. So I'll have 15 minus 6y minus y equals 1. I can combine my y's here, so that's 15 minus 7y equals 1. I'm going to subtract the 15 over. So now we've got negative 7y equals negative 14. Divide both sides by a negative 7, and y is equal to 2. Excellent. So step 3 is to solve the equation from step 2. Now, one very big word of caution here. It's easy to say, oh, I just solved an equation, I must be done, because usually when you solve an equation, you've got the answer. But we were solving a system. I was looking for an x and a y value. Okay. So I'm not done, I'm halfway there. I know one of my variables, but not the other. Okay. But that's okay, because once I know one variable, I can substitute that back in to get the other one. Okay. Now, because I've got such limited space here, I've erased a lot of stuff. I'm just going to remind you, our original system was x plus 2y equals 5, and we had said that meant that x was 5 minus 2y. And then our second equation was 3x minus y equals 1. Okay. Now, I can plug in 2 to any of these equations. This original one, or what's simplest is this one where I solved for x in terms of y. I think that's what I'm going to do. I'm going to say x is 5 minus 2y. That's going to be 5 minus 2 times 2. That's going to be 5 minus 4, which is 1. Okay. So that gives me my other value. Okay. So step 4 is to plug the answer to step 3 into any of the equations with both variables. And solve for the remaining variable. Running out of space. My goodness, we have y equals 2. Okay. Solve for the remaining variable. Okay, so once we've got that, we want to just state our answer. So I could say x is 1 and y is 2. That would be a perfectly acceptable way of stating your answer. But note, I boxed that and made it super clear, because sometimes what's happened is you solved for one variable at the bottom of one page, and then you did some more work and you solved for the other variable, and they're totally separate. If I have to go searching for what your answers are, you're not telling me very clearly what the answer is. Put them together. The other option is to give it as just a point. This would be the point 1, 2. One thing to be careful of here is a point would be an ordered pair. We actually found the y value first, but y comes second when I'm listing an ordered pair x comma y. So do be careful that if you list things as an ordered pair, you give things in the right order. Okay. So I'm just going to put step 5 up here, which is to clearly state the answer. I'm just going to put or sirs. In this case, we were working with 2 lines. If 2 lines intersect and don't completely overlap, they're going to intersect at one point. So it's pretty common to get just one solution in a situation like this. It's possible to have parallel lines, so you could get no solution. And it's possible to have overlapping lines, 2 different equations, but that give you the same graph. Turns out the equations are equivalent, it's just not always obvious from looking at them. And that would give you infinitely many solutions. Okay. But most often with linear systems, we're going to expect to see just one point. When we start working with curves instead of just lines, the number of solutions that we have is going to be a little bit more flexible. So we might encounter a situation where we have 2 or 3 solutions. So we have more than one without having infinitely many. And we'll see that as we start working through our nonlinear examples.